This video is for topic 1.11 in AP Pre-Calculus, taking a look at polynomial and rational functions and equivalent representations. In this lesson, we're really going to try to package together all that we know about finding wholes, vertical and horizontal asymptotes, zeros, and even engage in the conversation with slant asymptotes of rational functions. We'll also see some other interesting kind of add-ons, we'll say, as it deals with polynomial expressions and functions. As we get started, remember that h of x defined by some function of x over g of x, right? The quotient of f and g, right, is a rational function. If g of c is 0, then h of x has a vertical asymptote or possibly a whole at x equals c. So we want to take our first example and practice finding wholes, vertical asymptotes, and use that to be able to talk about the domain of the example. So let's start with the factored form. The numerator in our first example, x squared minus 4, can factor as a difference of perfect squares, x plus 2 and x minus 2. The denominator is the AC method, trinomials. We're trying to kind of fill in the puzzle, factors of 10 that add to 7. So that's going to be x plus 5 and x plus 2. So we can see here, because these common factors of x plus 2 will cancel out, more specifically, they cancel out from the denominator, we're going to have a whole at x equals negative 2, again, because those two are canceling out. We have a vertical asymptote at x equals negative 5, because of that factor x plus 5 in the denominator. So this means x cannot ever be that location of the whole or the vertical asymptote at negative 2 and negative 5. So if we have to find the domain, we want to say all the values on this function that x can be, right? So a simple way could say x cannot be equal to negative 2 and negative 5. In fact, kind of a fancier way to say this that you won't necessarily need to use, as we can say the domain is x such that x is not equal to negative 2 or negative 5. Okay, so you might have seen that before. But the preferred way is instead to use intervals. So x can be anything negative infinity up to negative 5, but not equal to, and negative 5 to negative 2, but not equal to, and negative 2 to infinity. So that's the better way to write our domain. Use interval notation. Just wanted to expose you to that set notation off to the side in purple. Okay, so similar example. This time we get to talk about zeros, vertical, horizontal asymptotes as well, and how they might affect the domain. Always want to factor it. The numerator will factor with that trinomial. So factors of negative 12 that add to negative 1. So that's going to be negative 4 and positive 3. And then our denominator has a greatest common factor of x. So if we factor that out first, if I just do that up here, we're going to get the quantity x squared plus x minus 20. And so common factor of x, and then factor that trinomial more, x squared plus x minus 20. So factors of negative 20 that add to 1, negative 4, and positive 5. Okay, so we can see that the x minus 4's cancel, so that helps us find a whole. So there is a whole at x equals 4. The zeros would be what our numerator, our leftover factors in the numerator set equal to 0, so the x plus 3. So a 0 at -3. That simply means it goes through or crosses or touches the x-axis. It's not an undefined value. In fact, it's a defined value. Okay, vertical asymptotes. Go to your simplified version. Those factors still left in the denominator. We see an x and an x plus 5. So I might just write those down here. So our vertical asymptotes would be where each of those are 0. So at x equals 0 and x equals -5. Horizontal asymptotes, we have to think about bottom heavy, top heavy, or power equal in those rules. This is bottom heavy because it's x cubed on the bottom versus x squared on the top. Bottom heavy always means we have a horizontal asymptote at y equals 0. So I might just make the note. Bottom heavy. Okay, so the domain, what can x be? Well, we know x cannot be equal to the location of the holes or the vertical asymptotes. So I'm just going to underline them in orange, the 4, the 0, and the -5. It can be anything outside of those values. So -infinity, oh, I should put it on my line here, -infinity to -5, and -5 to 0, and 0 to 4, and 4 to infinity. Oops. Okay, apparently my eraser doesn't work. Okay, so the last little bit, unfortunately, with the way that I am recording this video, I can't really show because I can't get to the calculator on this app. But please use this time, pause the video, and practice using your graphing calculator, right? So go type your function into the y equals and graph it. We should be able to do this more or less by hand, so I'll go ahead and start doing that over here. So we have vertical asymptotes at 0 and -5. We have a horizontal at 0. We have a 0 at -3, so we know it crosses the x-axis right there. Okay, and so then put it into the graphing calculator. You can kind of sketch the rest of it. I suppose I could get the location of the hole. So we know it's at an x value of 4. So if we go plug that 4 into the simplified version, which I'm just going to pencil in up here, we're going to get, what, 7 over 4 times 9 or 36, so super small number. So this would be the ordered pair of the hole at 4 and 7/36. So basically 0, right? Really, really close to it. So it might be hard to show, but there's my hole in blue. Okay, so again, use your calculator, look at your graph, use it to sketch, or you can do what we did in class the other day and try to graph it by yourself. But this is essentially what it should look like. You could probably make a lot better, more accurate sketch than me. Here I'm just penciling it in. So far in this lesson, it's basically review. We did add in just discussion or communication on how we would describe the domain using that interval notation. So this page, it's also good review. So if you're feeling good about this vertical asymptote, holes, horizontal asymptote, if you're feeling good about this discussion, it would be a great idea to pause the video right now and see if you can do example 4 and 5 on your own. Otherwise, here I go. So I want to look at the key features on the graph, namely the asymptotes and any holes and any zeros, to help figure out what my equation would look like. So I guess I'm in the habit of looking at my vertical asymptotes first. This function has a vertical asymptote at x equals 2. So that means the factor x minus 2 must be in the denominator. So you can see how I just write myself some notes to keep track of all of this. You could start writing the equation now if you want to, but this is what I do. Okay, there is a whole at x equals 4. So that means the factor x minus 4 should cancel from the denominator. So this is interesting, right? Because we know that there has to be at least one x minus 4 in the numerator and one in the denominator. But when they cancel out, there can't be any left in the denominator. That's the biggest thing. So this is where we maybe want to keep talking about like multiplicities on them and how do we know which is which. And it's a cool level of it that we can keep talking about. Okay, zeros. This thing has a 0 at x equals 3. So the factor x minus 3 must be in the numerator. My handwriting is really good here. There we go. And then lastly, we notice there's a horizontal asymptote at y equals -1. So this means that it must be power equal and that the ratio of those coefficients, so I'm just going to go coefficients -1. Okay, so if we put it all together, our function, if I kind of read my notes to myself, I know I have to have x minus 2 in the denominator. The x minus 4s have to cancel, so at least one in each. X minus 3 in the numerator. And then the ratio of the coefficients has to be equal to -1. And then this is where we did one like this in our 1.9 notes. And I'll just be honest and say that it probably didn't click with you, this whole k value that we have to find. So I kind of want to just overlook that for now until we feel a little bit better with this and we can talk about it. But as long as my coefficients in front of these reduce to a -1, it's good. So I'm just going to do -1 over +1 like that. A way that you would want to check for this is to look at the actual coordinate of that whole. So the whole has a coordinate, we're just going to estimate it at 4, -1/2. So what this means, this -1/2, if we plug a 4 into the simplified version of this function, which would be -x minus 3 over x minus 2. Okay, so if we plug a 4 in there, we should get a y value of -1/2 because of the location of that whole. So like I said, we did something like this in the topic 1.9 notes, but I didn't do it very artfully, and so this might be something we have to keep talking about. This works. So if we check it, if we plug in a 4 for x, we do get -1/2. So that means I don't have to change those coefficients to be anything else to help get the location of that whole correct. But this is one version of a function that would fit this graph. There might be many others. So that might be fun to explore a little bit. Okay, next, example 5. It's very similar. This one, possibly, I don't remember correctly, but possibly the first time we see as a group rational function that is in like 3 pieces, like we can see in the graph of number 5. So we start the same thing. We want to recognize where it has asymptotes and any holes to help write the equation. So I like to list those. So there is a vertical asymptote in a couple spots at x equals 0 and at x equals 3. So we know we're going to have an x minus 3 and a factor of x to make it 0. In the denominator. We have a whole at x equals 2. So the factor x minus 2 needs to cancel from the denominator. We have a 0, looks like at x equals 1. So the factor x minus 1 must be in the numerator. And then our horizontal asymptote is at y equals 0. So just, a little bit different than the example 4. Y equals 0 horizontal asymptotes means that it's bottom heavy, or the power in the denominator, the degree in the denominator will be bigger than in the numerator. So far, an x and an x minus 3 in the denominator, an x minus 2 in both, an x minus 1 in the numerator for 0. So if I just double check, am I bottom heavy? Degree in the numerator would be, I should say the leading term would be 1x squared. And in the bottom, it would be 1x cubed. So it looks like, yes, we are bottom heavy. So now we need to make sure that this equation has met all of the descriptions. Of course, we got all of the features, but then now what about the signs of the graph? What about the behaviors of the graph as, for example, as x approaches unbounded behavior to the left or the right, or as x approaches the infinities and things like that. Is there a need for more or different coefficients, positive versus negative, etc.? So this is kind of going into what we did in example 4 in the blue writing above to help figure out that there needed to be at least a -1 in the numerator. So I'm going to show this one a little bit different. You can use limit statements or analyze the behaviors with the limit statements. So if I just choose the limit, if I look at the vertical asymptotes, if I want to maybe investigate the behavior on the right side of that vertical asymptote at 0, this can help us make sense of any additional pieces in our equation to make this work. So I noticed that the behavior on the right side of my asymptote, so this section of the graph that I'm trying to draw blue, as we get closer and closer to 0 from the right, okay, following that blue arrow, our function is approaching negative infinity. It's approaching that asymptote, but the y values are always negative. So this means if we pick an x value directly to the right of 0, say like, I'm going to say like 0.1, and you could exaggerate that and you could say like 0.01, 0.001, right? But I'm just going to use this 0.1, 1/10 as an example. So if I were to plug that in, I'm just going to try to zoom in a little bit. If I were to plug that value into my function for x, would I get a negative value? That's what I want to check, because it should be if I get this pattern right. So if I plug in a 0.1, and this first factor, I'm just going to use symbols. 0.1 minus 2 is going to be a negative number. 0.1 minus 1 is also a negative number. 0.1 is a positive. 0.1 minus 3 is a negative. 0.1 minus 2 is also a negative. So if I look at just my symbols of this, I'm going to get a positive number in the numerator and also a positive number in the denominator. That does not fit the behavior we said it was going to over at, gosh, I just want a pointer, there we go, over at this limit here. As x gets closer to 0, the y value should turn negative, and increasingly negative the closer we get. 0.1, right, think about it, that's like right there on the graph, that should be a negative y value, but that's not what we got. So we need to add in something to our equation that's going to make this be a negative value. We just need one more negative in either the numerator or the denominator, and we can just add it in the numerator. Okay, so that negative is going to now make it be a negative value and fit that pattern correctly. So that's one way to think about it, is look at your behaviors at asymptotes. And there's more patterns with this that has been kind of talked about in class a little bit. So like I said, and a common theme throughout this is there's more to explore. There's more and maybe slightly different types of problems that we should look forward to encountering as we practice this. So next in this topic, we get a chance to dive a little bit deeper into those slant asymptotes that have come up. So remember that in a rational function, if the degree of the numerator is one more, exactly one more than the degree of the denominator, then the rational function must have a slant asymptote. So we know as x approaches unbounded behavior to the left or the right, our function is also unbounded, but it will approach that that slant asymptote. And so let's learn how to find those. Okay, so the graph above here, in the beginning of your notes, we can see has that slant asymptote. Okay, the function k of x is what's graphed above, so you can see that equation, and its factored form. Because the x minus 2's cancel, from the denominator there's a hole at x equals 2, there's a vertical asymptote at x equals -1 because of that denominator factor of x plus 1. Does not have a horizontal asymptote because the degree in the numerator is larger than the denominator. We call it top heavy. But because it's x to the third over x squared, one more in the numerator in comparison to the denominator, it must have a slant asymptote. To find the equations of slant asymptotes, we can use long division. So let's do a quick review of what long division is. We're going to do it numerically first. There are a lot of different algorithms for long division, and so here's one of them. Hopefully you've seen this in your lifetime. If we took 676 and divided by 21, we are going to sort of essentially break this up into pieces. And so instead of thinking how many 21s fit into 676, let's just figure out how many 21s fit into 67. So it looks like 3 of them, because 3 times 21 is 63. So now we're going to subtract that to see what our remainder is, because it didn't go in a perfect amount. 67 minus 63 is 4. Okay, 21 cannot divide into 4, it's too small, so we bring down the next digit. So now same thing, how many 21s fit into 46? Well, for sure 2 of them, because 2 times 21 is 42. So subtract, we have a remainder of 4. You know, this is where if you start learning decimals back in elementary school, like we could say this is 0.0, so now we could bring down the 0 and keep going. But we're just going to stop here for how it connects to our algebra in a minute. So we would say our quotient is 32 and our remainder is 4. So this is always, whatever you have left over is always the remainder. And so we'd write our answer as 32 and 4/21, because that remainder of 4 still needs to be divided by 21, and in doing so, that's where we would come up with those decimal places. But a decimal is just a fraction, as long as it has a pattern or terminates. So let's write it as a fraction. Okay, so you should have learned how to do polynomial long division with the same algorithm. So let's look at that one. 6x squared plus 7x plus 6. Okay, we look at this, what's called the dividend, what we're dividing. We want to make sure that we have all of the powers accounted for in descending order. So if you start with an x squared, we want our next term to be an x, and then an x to the x to the 0, and so on. So all good there. The divisor, this 2x plus 1, goes on the outside. Okay, so just like with our numeric long division, we're just going to go one term or just a couple numbers at a time. So we're going to go this first term, 6x squared, and divide it by the first term there. Sometimes when I teach this to students the first time they see it, I tell them, if that's hard for you to visualize, jot down that division problem off to the side of your work. 6x squared divided by 2x is 3x. And notice I'm staying organized, and I'm putting those, because I got an x, I'm putting it above the other x's. I'm going to have a nice column of x's, a nice column of x squareds, a nice column of numbers throughout my work. So now multiply that 3x back out to help us see what we need to subtract in this spot right here. So 3x times 2x is 6x squared. 3x times positive 1 is 3x. Subtract it to find our remainder. The 6x squareds cancel. 7x minus 3x is 4x. Bring down the next term and start over. 4x divided by 2x, again, jot it off to the side if you feel like you need to. 4x divided by 2x is 2. Multiply that 2 back out. 2 times 2x is 4x. 2 times 1, 2. Subtract it to find our remainder. 4x minus 4x is 0. 6 minus 2 is 4. So again, because I don't have any more numbers up here to bring down, we know this is our remainder. So our quotient is the 3x plus 2 we got up at the top. Our remainder is 4. So same thing, we're going to write our quotient, which really just means the answer to the division problem, and the remainder in that fraction form, which communicates it still has to be divided, but we can't simplify it. So because it's a positive 4, we're going to go plus, and then 4 still divided by that 2x plus 1. Okay, so now that we know how to use the long division algorithm, let's see how it's used to find the slant asymptote. So example 6. We know it is top heavy by 1 degree, so there must be a slant asymptote. And so we're going to just start with dividing it right away. Okay, first term, 6x squared divided by 2x is 3x. Distribute that back out. We're going to get 6x squared plus 3x. Subtract it. The 6x squareds cancel. 1x minus 3x is negative 2x. Bring down that plus 5. Start your division over again. Negative 2x divided by 2x is a negative 1. Distribute it back out. Negative 2x minus 1. And so our remainder, 5 minus a negative 1, that's really 5 plus 1, or 6. So we could write it like this. H of x, like, right, so I'm writing an alternative version of this function because we completed the division. So this is still an equivalent representation of h of x. That's why this topic is named as it is, the equivalent representations. So taking this rational function, we can write it after completing the division as 3x minus 1, and then plus 6 over 2x plus 1. So by definition, we can't call that a polynomial function because there is an x in the bottom of a fraction there. But these two expressions or equations mean the same thing, right? Like if we plug in an x equals 2 here and then plug in an x equals 2 here, we should get the same value because they are the same functions. But the cool part about this is this second representation directly shows us the slant asymptote. It's just that first chunk of the actual polynomial piece of that function. So the slant asymptote is at y equals 3x minus 1. All right, let's see another example of this. Example 7, we have our rational function, top heavy, cubic on top, quadratic on the bottom. So we know there's going to be a slant asymptote. Let's work on our factored forms of everything. Okay, so it looks like my denominator is a little bit easier to factor right away. Factors of 6 that add to 7, that's going to be 6 and 1. So x plus 6 and x plus 1 in the denominator. My numerator has a greatest common factor of x. I'm going to factor that out first and just show it up here. So now it's factors of 12, negative 12 that add to 4. So that's got to be a positive 6 and a negative 2. So here we can see the x plus 6s are going to cancel out. So there isn't a spot for it. I'm just going to add it over here. We know there's a hole at x equals -6, which means there's a vertical asymptote at x equals -1. There is no horizontal asymptote. I'm just going to say none because it's top heavy. And the slant asymptote we will find from the long division, which I'm going to do over here. Okay, so we are going to go from the simplified version of this because with the factored form, the x plus 6's cancel out. So our function g of x simplifies to x times x minus 2 over x plus 1. And so if I distribute that numerator out, we're going to get x squared minus 2x. So that's what I'm going to do the long division with. I don't want to do the long division with the original representation of the function because those x plus 6's cancel out. Why do it with that, more expanded or larger representation of it? We want to do the more simplified one. Okay, so our long division is going to be using the divisor of x plus 1 and then x squared minus 2x. So now x squared divided by x is x. Distribute it back out, we get x squared plus x. Do a little subtraction. X squareds cancel. -2x minus x is -3x. This is where we'd bring down the next term. Well, there isn't a next term except for 0. So we can use that as a placeholder. -3x divided by x is -3. Distribute it back out, -3x minus 3. And so our remainder is 3. And quite honestly, I don't even really care about that. The quotient up at the top, the x minus 3, is telling us what our equation of the slant asymptote is. So we know our slant asymptote is at x minus 3. Okay, last couple examples are good ones. Multiple choice and then a drawing one, which is I really like example 9. So excited for that one here. We have a rational function d of x in mostly factored form for us. Looks like we might be able to do a little bit with the denominator, and it's simply asking which of the following is correct about the function. If I scan through the options, it looks like we're trying to analyze the features of the graph. Horizontal asymptote, holes, vertical asymptotes, possibly slant asymptotes. Okay, so if I process that first, factor the denominator, this would be x minus 1 times x minus 1. So I can see one of those x minus 1's cancel, but because that factor x minus 1 doesn't cancel from the denominator, there's still an x minus 1 left. It's not a hole. So this tells me there are no holes. Okay, so let's see if I can cancel some choices out. Looks like choice A says 1 hole, so that can't be true. Choice C also says 1 hole, so that also can't be true. So it could be B or D. Let's keep going. Let's see the vertical asymptote in this thing, because of that factor x minus 1 in the denominator, there is a vertical asymptote at x equals 1, and there's only one vertical asymptote. So that should answer our question for us, because that's the big difference between choice B and D. B says there's 2 vertical asymptotes, but that's not true. There's only 1. So it's got to be D. So let's just make sure the rest of this makes sense. Yep, no holes, 1 vertical asymptote. How do we know there's 1 slant? Well, the lead term in the numerator, if I take, let's highlight it here. If I take the 2x times the x times the x, our lead term is going to be a 2x to the third. And in the denominator, it's a 1x squared. Exactly 1 more degree in the numerator in comparison to the denominator, so there is a slant asymptote. All right, our last one, using limit statements to help create a picture. These are really important questions, I think, because they're really causing your brain to work almost in reverse order than what we have been doing. These can be really challenging, so I really hope this example is helpful to you. Sketch a picture. All right, so what I'm paying attention to when I read these limit statements is what is x approaching? And are there any limit statements that would kind of go together to show the same thing? The first two go together because we're talking about the limit as x approaches infinity and negative infinity. And most important, both of them are showing unbounded behavior on the function f. So these are telling me, these are showing the slant asymptote. Okay, so as x goes to the left, so if I just draw arrows, okay, the function is going towards negative infinity. So somewhere over here on the left, it's going to be pointing down, and it's going to be doing so at a slant asymptote, possibly like that. Okay, it might slant at a different order, but something like that over there. Okay. So what about limits 3 and 4? Well, they're looking as we approach a particular x value at -1. They are also unbounded behavior on the function f. And they're both, looks like negative infinity. So it's telling me on the left side of 1, the y values get more negative, but also on the right side of 1, the y values get more negative. So this is showing a vertical asymptote at x equals 1. I'm sorry. Yes, -1. Gotta look carefully there. So we know there is a vertical asymptote at -1. And we know on the left side and the right side of this value, the function is approaching negative infinity. So what I can confidently sketch right now is something like that. So now we got to figure out the slant asymptote. I am just going to kind of arbitrarily do this and then go back and check it to help show you my thinking. So what if the slant asymptote sloped in the positive direction? Because, right, we don't necessarily know that yet. Arguably we do, but that's what I'm helping us process. This can't work because this left chunk would have to face like this, okay? And that doesn't fit our limit number 2. It says as x goes to negative infinity, the y values go up to positive infinity. This arrow on this side is showing as x gets more negative, y gets more negative. But that's opposite of what it should be. So that tells me right there, if I can undo my pictures, there we go, that the slant asymptote has to go the other way. Okay, and you could draw it at whatever slant you want. So I'm just going to kind of arbitrarily say this. Okay, so that kind of left chunk would have to follow in this sort of pattern, and now it works. As x gets more negative, the y's get more positive. That's fitting our limit statement number 2. So then on the other side of that horizontal asymptote, it's got to go like this. So let's check that one. Does that work with limit statement number 1? As x approaches infinity, y's approach negative infinity. As x gets more positive, y gets more negative. It is going to the right but down. That works. Okay, so it's going to look something like this. The slant asymptote might have a slope that's a little bit different than the one I picked, but this is the general shape of it. Okay, that's as far as we're going to go in this video for topic 111. We'll finish the rest of it next time. Thanks for watching.